Okay, so we're recording this session now, and let's continue with the practical work, and I'll simultaneously try to teach you all some theory as we go along. Okay, as we come across new concepts, I'll jump back into the theory. Any questions or doubts from the previous class? Okay. And since nobody,
How to save console?
yeah, I'm coming to that. So I think I haven't tried this myself. Like, you can try this, try going to new project and start a new project. And okay, so this will be your new project. You can set your working directory and so on. Okay, and name the project and then proceed from there. So everything that you do will be saved in that project. And then the next time you come in, you can just do open project and continue from there. Okay. So I think you can try that. Okay, just as a backup, in case that doesn't work, you can just save all your data to a Word file, or you can just do save workspace or save all. Okay, so that is here. Or you can do new session and then try that. Okay, start a new session, then at the end you can do save workspace.
Okay, ma'am.
Just try that. Does anyone have any suggestions for that? How to save your entire session and then continue from there in the next session itself?
Actually, the thing is, if we don't write the codes in console, then we can save the codes and the console part.
Okay, so you're saying you'll write it in a script and then run the
Yeah,
commands
if
from
we,
there, is it?
yes, ma'am.
Okay. Yeah, you can do that. But in case you want a reference, yeah, actually you can do that. That's also fine. You can do, uh, you can work with a script and then continue from there. Okay.
Mm-hmm.
So where are you writing the script part from? I'm not able to see it right now. I've done it earlier, but I don't.
I
Yeah,
guess we
here.
can choose new
Yeah, yeah.
file.
Okay, so from here, you can do new file and then R script. Okay, and then continue from there. So then you can just run the commands every time and you'll get the results. Okay, so you can do that also. So let's continue with what we had done in the previous session. Okay, so here I've just cleared it so that I have less information here in the environment part. Okay, so you can clear your environment using this command. So the previous things which were there when we had used X11, seats, X13 and so on, all those things will go, and I'm trying to minimize the information that's here. Okay, so that's why I've cleared my environment. If you want to do that, you can do that. Then just load all the packages that you need, the same packages that we used the last time. All right. Have you all already loaded it? Or do you need some time for this? Okay, load the data set and the packages that you'll be using.
Yes, ma'am. The one you told in the last class that we have done.
Okay, fine. Okay, so we'll continue from there then. Okay. So I'll just convert my data to logs. You all might have done that already. Okay.
Yes, ma'am.
Yeah. And then I'm just quickly decomposing my data so that I can get it back to the detrended data that we're working on. If you have cleared your workspace and so on, you can just follow along and bring it back to this point. Okay, so this is a plot of our detrended data. Okay. Can I continue from here, or do you want me to wait?
Ma'am, please wait.
Okay.
Ma'am, could you just scroll a little up? Thank you, ma'am.
Okay, those who are typing in the commands, just let me know once you have reached this point. Okay, once you have detrended the data and plotted the data, just let me know.
Yes, ma'am.
Okay.
Done with it.
What about the rest of you? Can we continue?
Yes, ma'am.
Okay. Okay, then just out the name of the data. Okay, this detrended data, just so you can take a look at the observations. Here you will find that there are some missing observations. So this is the point at which we had stopped in the previous class. Okay, how to get rid of these missing observations. Okay, so you can see that because that moving average would have been used to calculate the trend, okay, you have a certain number of missing observations here, 6 right at the beginning of your data set and 6 towards the end. Okay, so let's just use this command. This will tell you whether there are missing observations in your data. You can already see it, but at any other time, you might find this command useful. Okay. So when you ask, is some observation missing, okay, in this particular data for this variable? So it's telling you that for the first 6 observations, missing is true. Okay, so these observations are missing, and for these last 6 observations again. Okay, so at any other point of time, if you don't want to see all the numbers, you can just see whether which ones are missing. Okay. Then after this, what you can do is just type this. So we're trying to omit the missing observations and delete them.
Ma'am, I had one doubt.
Yeah.
Ma'am, can we, instead of deleting them, put mean or mode instead of their values?
Sorry, can you just repeat that?
Ma'am, what I'm saying is, instead of deleting the missing values, can we replace them with mean or median?
No. Okay, it would be preferable, since we have detrended the data. We don't want to, what do you say, input any other sort of information there. Okay. In other cases where you have data already with some missing observations, you might want to fill in those gaps in your data set. Okay, so there you can probably use some sort of extrapolation method to fill in those missing values. But here we won't do that. Okay, it's better not to do that.
Ma'am, a follow-up question. What is the criteria for deciding whether we have to delete the missing values or substitute them via extrapolation?
I don't think there's any criteria as such. For example, let's say you have a very small data set. Okay, in our case, we had 144 observations, and now it's dropped down to 132. Okay, that's still a fairly good number. Now, suppose you had a very small number of observations, maybe like 30 or 40 observations or something like that, then you might find that the loss of observations might be costly to you. Okay, so in that case, you might want to fill in the missing values if you have a very small data set. I don't think there's any criterion as such. In other cases where you download a data set and you already find that there are some missing observations, okay, there you might want to fill in the gaps so that you don't lose out on data. Okay? So there, where you already have data which has missing observations, here through some manipulation we've come across these missing observations. Okay, which is that we decompose the data and we try to estimate a trend, fit a trend, and because of that detrending process, we've lost out on some data. Okay? But here, if you already have data where there are missing observations, then you can try and extrapolate. Okay, given your sample size, those are things that you might want to consider. How costly will it be to lose information for you? Okay.
Okay, ma'am. Thank you, ma'am.
So let's come back to this. Now, when you type this, okay, let's try and check, are there missing observations now in this? Okay, so we don't have any missing observations now. Okay, you can see that all the entries have been returned as false. Okay, so we've overcome this problem of missing observations, and now we can continue. Of course, we've lost some data in the process, okay, but I think 132 is still a good number to work on. Okay, so let's continue from there. So now let's just plot, it'll be essentially be the same thing, but let's plot the data. Before we do that, let's quickly confirm. We had done this in the previous class also, but let's just confirm once again that our data is stationary. Okay, because we want to plot the ACF and PACF on stationary data, not on non-stationary data. So let's just run a quick test of stationarity, a unit root test. I'll discuss this in greater detail in tomorrow's class. Okay? So we are testing whether this time series now is stationary. Okay, so our null hypothesis here when we are using this ADF test is that
Ma'am,
the
just a doubt. ADF test comes under which package?
ADF test right now, I think it's coming under T series, okay? But there are multiple packages actually to do these sort of unit root tests or tests of stationarity.
All right,
But I
because
think
I think I'll have to load some package for this ADF because it's not showing up.
you loaded all these packages, the ones that I had typed in earlier.
Ma'am,
Stats.
I have loaded stats, ggplot2, forecast, and XTS. Okay, you've done T series. All right.
Yeah. You just load T series, you'll be able to run this test. Okay, so let's check. Now the null is that the series is non-stationary, okay, or not stationary. And the alternative hypothesis is that the series is stationary. Let's just check quickly. Okay, so you can see from the p-value that we're clearly rejecting the null hypothesis. So our time series is now stationary. Okay, so we can go ahead and plot the ACF and the PACF. Okay, I hope all of you have got this result.
Ma'am, could you just give us 1 second?
Yeah.
Ma'am,
Yeah. Yes.
ma'am, is it possible that after removing the trend too, we can have a non-stationary series?
Yes. Okay. This is something that again I'll discuss in tomorrow's class.
Okay, ma'am.
There, you can have a trend stationary process or time series where once you remove the trend, the series becomes stationary. Otherwise, there could be other types of stationary processes, okay, or other manipulations that you can do to make the series stationary. So we'll discuss this in greater detail in tomorrow's class.
Okay, ma'am.
Okay, let's just quickly confirm this result again with the KPSS test. Okay. This also, I think we had done it in the previous class. I'm just repeating it again to confirm. Now, since we've removed the trend, what we want to check for is level stationarity. Okay, that the time series as it is stationary. Okay, so if you remember from our discussion in the previous class, for the KPSS test, the null is that the time series is stationary and the alternative hypothesis is that it is non-stationary. Okay. So our null here is that it is level stationary, that this time series, the detrended series, okay, of air passengers data, it is stationary. So now here, if you look at the p-value, we are not able to reject the null, which means that our time series is now stationary. Okay, so we can go ahead and plot the ACF and PACF. Okay, just type in this command also and get the result. And let me know once you finish, then we'll proceed.
I'm so sorry, what does level mean out here?
Level means that you take a time series as it is. Okay, so for example, this DTLY variable, it's basically the detrended variable. Okay, from that air passengers data, we've removed the trend. Now the time series that is left, I've called it DTLY1.
Yes, ma'am.
So as it is, this data is now stationary in levels. Now suppose it was not stationary in levels, and if I took first differences, that means I'll just call this variable y, okay, now to simplify it. If I take yt minus 1, okay, so if I take the first difference, then it becomes stationary, then it's called a difference stationary process. Okay. So a time series could be stationary in levels or it could be stationary in differences.
All right. So, ma'am, what we are telling the code is that we have already leveled the data, and there's no need for them to try and level it. Is that right?
I wouldn't put it that way. We are just testing that the time series as it is in levels. This is in levels itself. So we are testing that in levels it is stationary. Okay? There's another test which we did the last time. It could be trend stationary also. Okay, that's a test we had implemented in the last class. If you watch the video from the last class, you will see that. Okay, so this one again I'll discuss in greater detail tomorrow. Okay. So here, after detrending the data, removing the trend, we have found that the series as it is stationary. Okay, so we don't have to do any further manipulation to this series to make it stationary. Okay, can I continue from this point now?
Yes, ma'am.
Okay. Okay, if anyone wants me to stop, then just let me know. Okay, you can use this command, or wait, there are a series of or variety of commands that you can use. This just saves time. Okay, so last time what I had asked you to plot was this command. It will come from the stats package. Okay. So if you type ACF and the name of the variable, okay, for which you want to plot the ACF. So R will keep prompting you, so you can just click on that prompt and you won't have to type the name of the variable. Okay. So let's plot the ACF first. Okay, now when you see it, okay, this is a plot of the autocorrelations at various lags. Okay, now it looks a little funny because you can see lag 0.5, lag 1.5 and so on. Okay, so this might look a little funny. Let's just look at the PACF also, and then I'll show you one or two alternate commands. Alternative commands. Okay, so let's plot the PACF also. Okay, so this shows you a plot of the partial autocorrelations at various lags again. Now, instead of this, you might want to use a couple of other commands. Okay. You might want to use this. Okay. So you'll get a slightly better looking plot, basically. Okay, let's plot it for 12 lags. Okay. So here this problem is not there. Okay, you don't have 0.5 lags and so on being shown. Okay, so we'll work with this one. Okay. So first let's look at the ACF, then we'll plot the PACF. Okay, remember you need to plot the ACF and PACF for stationary data. Okay, are all of you looking at this plot of the ACF?
Yes, ma'am.
Okay, so now that you're looking at it, remember that we have monthly data. Okay, we are using monthly data on air passengers, the number of air passengers in thousands. Okay, so if you look at the ACF, what sort of pattern is it indicating? Okay, remember that the ACF will generally help you to identify the MA order of the process or the time series. Okay, just look at your own plot. Now what you'll notice is that there's a sharp spike at lag 1, right? Okay. Then at lag 2 again, there's a statistically significant spike. If it's moving outside these bands, okay, that means the autocorrelation is statistically significant at that lag. So at lag 1, we can see that it is significantly different from 0, the autocorrelation. At lag 2 also, it's moving slightly outside this band. Okay? So you might think that we need to maybe incorporate two MA terms here. Okay? Now at the same time, you can see that there's some sort of an oscillating pattern. Okay? It's not geometrically decaying. You don't see the decay only on one side. And in fact, it is oscillating and at higher lags. For example, at lag 12, you're seeing a bigger spike here. Okay? I hope all of you are able to see this in your data.
Yes, ma'am, because it's annual data, so what happened 1 year ago is quite important.
Yeah, this is monthly data. Now, the fact that you're seeing a sharp spike at lag 12, okay? Now, this is characteristic of data which is showing seasonal patterns. Okay? Now, if you just go back to the previous plot, I'll just close my plot. In your own RStudio interface, just go back to the previous plot. Okay, you can just use the arrow to go back to one of the previous plots where you plotted this variable dtly. It's essentially the same thing but with missing observations here. Okay, so just look at the plot of dtly. You can see that there are clear seasonal patterns. Remember, we did not seasonally adjust the data and use it. Okay? So here this data is still showing seasonal patterns. Now come back to the ACF plot. Okay? Now the fact that you're seeing such a sharp spike at lag 12, that is because the data is showing these seasonal patterns. Okay, so the seasonal pattern is being repeated after every year. You will notice that there's a sharp spike and then the seasonal pattern basically repeats itself. Okay? Since you have monthly data, you will see the spike at lag 12. Now, if you had quarterly data, then if the data was showing seasonal effects or patterns, you would have noticed a sharp spike at lag 4. Okay? So this is characteristic of a model known as a seasonal ARIMA model. Okay? So here I'll just delve into a bit of theory. Okay? Before we do that, we'll just plot the PACF also. Okay? If you're not following me at any point, you can just let me know and I'll just repeat or try and explain again what is being said. Plot the PACF for the same set of data. Again, you can use 12 lags. Okay, if you want, you can use 24. Okay? It's up to you how many lags you want to use.
Ma'am, sorry to ask, what does the GG stand for? I'm so sorry.
GG is for this GG plot package, right?
Okay, GG plot.
Okay, so again, if you look at the PACF, now just zoom in on your PACF. Okay, you can zoom using this part here. Okay, so just zoom in on your PACF and look at it. So here the PACF will generally help you to identify the AR order of the particular series that you're looking at. Okay. Now we can see that there's a sharp spike at lag 1. Okay, so we might expect that we'll be including an AR1 component. Okay, this may be possible. Okay. So this is one of the options that we have available to us. Then if you look at the pattern here, there's no real clear pattern. Okay, so if you remember that table which I had shown you all earlier when we were discussing the theoretical ACF and PACF, there it seemed very clear cut. Okay, that in the ACF you will see geometric or oscillating decay up to lag Q, and or after lag Q, the ACF will begin to show geometric decay, and that will help you to identify the AR order of the series. Similarly, for the PACF, you will find that for an AR1 series, after lag 1, the PACF will cut off to 0. Okay, so that would have helped you identify what is the order of the series. But in practice, it's never very clear cut like this. Okay, it will never be close to the theoretical PACF, and you'll see a lot of different patterns which will be very likely to confuse you. Okay, so generally you have to experiment a lot, and it's a process of trial and error which will help you to generate the best fitting model. Okay. So here also maybe we are not getting a very clear pattern or idea from the data itself. But again, what you'll notice is that there's a sharp spike at lag 12 in the PACF. Okay, so this is again indicative that there are seasonal patterns in your data. So let's just go back to a bit of theory. Okay, so let's look at, I think, this is available online. Okay, so I'll probably try and share the link with you all in through your mail. Okay, but for now, we'll just look at this Word file. Before that, let's just look at what I had shown you all earlier. So in general, for an ARMA PQ model, okay, so the ACF will show you decay either direct or oscillatory beginning after lag Q. Okay, this is what I was mentioning. And the PACF will show you decay either direct or oscillatory beginning after lag P. Okay, so if you look at these, what we've seen is that there's a positive spike at lag 1 and even at lag 2. Okay, but at lag 2 it was mildly significant in the ACF. Okay, that's what we found. Just look at your ACF again. Positive spike at lag 1, slightly significant spike at lag 2. Okay, so given this, just assume for now that we might be able to start our experimentation with the maybe MA2 model. So the MA order, we can experiment start with MA2 or even MA1. Okay, if you ignore this, if you think that it's very mildly significant, then if you look at this table again, decay either direct or oscillatory beginning after lag P. Okay. Now let's look at the PACF. You'll find that generally for the PACF for an ARP model, there are spikes through lag P. Okay. For MA, you'll find oscillating decay or geometric decay. Okay, so let's see what we've got here. Okay, just look at your PACF now. Okay, so here you're seeing a sharp spike at lag 1. Okay. So that might indicate that you're looking at an AR1 process, okay, the non-seasonal component. But again, in the PACF, you have a spike at lag 12. Okay, just remember this. So what we are looking at is not a simple ARIMA model, but it's a seasonal ARIMA model where there are non-seasonal patterns as well as seasonal patterns. So I'll quickly take you through a little bit of theory again. Okay, then we'll look at the other Word file that I'd mentioned. Okay, I'm just zooming in here. So generally, what we were looking at earlier was just this part. Okay, just follow my cursor. We were looking at an ARIMA model where PDQ indicates the order of the model. This P indicates the autoregressive order of the model. D indicates whether the data is stationary or not and how many times you have to difference the data to make it stationary. Okay, so this will be the order of differencing, the small d here. So now in our case, what we found was once we removed the trend, the data became stationary. So we didn't do any differencing. Okay, we didn't take a first difference. That is, we didn't take DTLY1 minus DTLY1 at the previous time period. We didn't do that. Okay, so because of this, the order of differencing in our case is 0. Okay, and then you have Q, which is the MA order of the time series or the process. So this refers to the non-seasonal part. Okay. Now you could also have seasonal effects or seasonal patterns that you see in your time series, which may actually interact with the non-seasonal parts of your time series. So since we did not seasonally adjust the data, you could still see those seasonal patterns in your data. Okay. So here we might want to fit what is known as a seasonal ARIMA model, because we want to take into account the fact that there is seasonality, or there are seasonal patterns in our data. Now, even if we had adjusted our time series, you'll find that in many cases, most people seasonally adjust their data and then they proceed to work with it, okay, estimate their model and so on. But there's no guarantee that once we seasonally adjust it, for example, using X11 or X13, if we had seasonally adjusted our data, it's not necessary that all the seasonality would be removed from the data. Okay, there might still be some seasonal patterns. But generally, people just assume that the seasonal pattern is gone and then they work with it. But if you're modeling your ACF, PACF, and you find spikes at the seasonal lags, okay, which means if you have quarterly data and you find spikes at lag 4, lag 8, lag 12, and so on, okay, multiples of 4, then it'll indicate that there are seasonal patterns in your data still. If you are working with monthly data, okay, and you find that in your PACF or ACF, you have spikes at lag 12, then lag 24, okay, lag 36, and so on. That will indicate that again there are seasonal patterns in your data, because at all the seasonal periods and multiples of the seasonal periods, okay, at those lags you have sharp spikes indicating there are autocorrelations in your data, okay, at those seasonal lags. So you might want to exploit this information and then carry out your modeling process. Okay. So here we might want to fit what is known as a seasonal ARIMA or SARIMA. Okay, the abbreviation for this is SARIMA. You'll find other abbreviations which will sound funny, but they're basically taking into account, in this case, the seasonality of your data, the seasonal nature of your data. Now, for a SARIMA model, okay, you will define or abbreviate the model this way. So this will show you the order of the non-seasonal part of your model, and this part here will show you the seasonal order of your model. So the P here will indicate how many autoregressive, seasonal autoregressive terms are there in your model. Okay, for example, I might have, if you look at these models, you'll be able to understand it. Okay, so this is one example here. Okay, this is a purely seasonal model where you don't have seasonal as well as non-seasonal components. So here we are saying that YT depends on its fourth lag. Okay, this is for quarterly data, since it depends on its value in the previous quarter. Okay, so this becomes a purely seasonal model. There are no non-seasonal parts. For example, it does not depend on YT minus 1 and so on. Okay, so here also, if you look at it, the moving average term, okay, you have 1 at lag 4 again. Okay, so this is again indicative of a purely seasonal model. Okay, there are no non-seasonal terms. But if you have seasonal patterns which interact with non-seasonal patterns in your data, then you will have both the components, the non-seasonal components as well as the seasonal components in your model. Okay. This might sound a little confusing, but if you look at the equation, you'll be able to understand. Okay. So taking quarterly data again, we are saying that YT, this time series, it depends on its first lag. Okay, depends on its value at lag 1, then the error at lag 1 again. Okay, so these are the non-seasonal components. But since I'm telling you that we have quarterly data and YT depends on the error from the previous season. Okay, so here this will indicate that this is a seasonal component. Okay, so for quarterly data, if you have YT or the time series being dependent on the errors in the previous season or the autoregressive components from the previous season, that will indicate that there are seasonal patterns in your data. Okay. Now, if you look at this particular equation, okay, these terms are entering the equation additively. Okay, the seasonal as well as the non-seasonal components, they are entering the model in an additive fashion. You're adding them in. Okay. Now, how will you designate this model? These are some ways in which you will come across these sort of models. So it might be referred to as an ARMA. Okay, since it's a stationary time series, you don't have to difference it. So instead of writing ARIMA, where D is equal to 0, we are just writing ARMA. Okay. Now the number of autoregressive terms, okay, is 1, and the number of moving average terms that we've included is 1, and we have the moving average term at lag 4 itself. So to indicate that, we've just put this, okay, to indicate the number of moving average terms and at what lags we are putting them in. Or we can indicate it this way, okay, ARIMA 101, okay, which means that we have one non-seasonal autoregressive term, this term here, yt minus 1. Then the order of differencing is equal to 0. We haven't differenced our data because it's already stationary. And we have one non-seasonal moving average term, which is et minus 1 here. Okay. Now this bracket here indicates the seasonal components. So here you have these seasonal components being 0, 0, 1, which means we have no seasonal autoregressive terms. So I don't have yt minus 4 here in my model, okay? Or I don't have yt minus 8. So because of this, there are no seasonal autoregressive terms, and the order for the seasonal autoregressive component is 0. Okay? Similarly, I haven't taken a seasonal difference. Okay? I'll explain what that is in a moment, but there is no seasonal differencing of the data to make it stationary. So because of this, the seasonal order of differencing is also 0. Okay? And then the number of seasonal moving average terms, okay, you have one seasonal moving average term here, okay, et minus 4. So you have one written here. Okay? So by looking at the numbers in brackets, you'll be able to understand what are the lags you've included in your model and whether there are seasonal terms or non-seasonal terms. Then again, if you look at this model, it's giving you the same similar information. You have one autoregressive non-seasonal term, okay, and one seasonal autoregressive term, yt minus 4. And you simply have one non-seasonal moving average term, which is captured by this here, 1. Okay? And since your data is already stationary, you did not need to difference it. Now in the Sarima model, you'll generally find this notation. Okay, so here, since we are looking at quarterly data, you'll find this m here will be equal to 4. Okay, so I forgot to put that in. When I'm sharing the notes, I'll put it in. Okay, so this will indicate that you're looking at quarterly data where the seasonal pattern repeats itself after 4 periods. Okay. So, or there are how many observations, seasonal observations are there in a particular year, or number of seasons in a particular year. Okay, that is what is denoted by M. So you'll be able to denote your Sarima model this way. Okay, and you can put in the autoregressive moving average orders and the order of differencing based on your particular model. Now, the seasonality could also be multiplicative. Okay, but before we come to this, just look at this part. Okay, what does it mean to difference a particular series, time series? Okay, so if you're doing non-seasonal differencing, okay, it's generally indicated this way. So if you're taking the first difference, okay, we will assume the value 1, and you'll be taking yt minus 1. Okay, so this gives you the first difference of your data. And generally with most time series, what you will find is that a first difference of the data makes it stationary if it's not already stationary in levels. Okay. Now, if you're taking a second difference, it means you're just taking another difference of the first difference data. Okay, so that is what is being shown here. You first difference the data and then take the difference of that. So you're differencing twice. So when you do this, okay, this is how you're differencing the data, or these are the terms you'll be writing in your equation. Okay, so finally it reduces to this. If you look at it in the form of an equation, okay, so this will give you the second difference. Basically, you're differencing the data twice in order to make it stationary. Generally, you can decide the order of differentiation based on tests of stationarity, which we'll discuss in tomorrow's class. So if you do a first difference and then you test for stationarity of the data, if you find that the series is still non-stationary, then you can go in for another difference. Okay, but in most practical work or applied work, you'll find that most people don't difference more than twice. Okay, it's not required most of the time. And it's actually very difficult to interpret this. For example, you can interpret this as the change. Okay? The change in the variable from one period to the next. Now this is the change of the change. Okay, but how do you interpret a third difference? It's a little hard to make sense of. Okay, so generally most people will find that their data becomes stationary after a first difference or at the most after a second difference. So we generally don't need to do more differentiation. Okay? Now, if you're seasonally differencing the data, if you're not able to follow at any point, you can stop me and ask questions. Okay. Now, yeah, okay. Yeah, for seasonally differencing your data, again, you can indicate the fact that you're taking a seasonal difference this way. Okay, so if you're taking a first seasonal difference, then with quarterly data, you'll be taking the difference of yt minus 4. Okay, its value from the previous season. Or at the seasonal lag, you'll be taking the difference. Then if you're second differencing your seasonal data, okay, or a seasonal second difference, it'll just mean you're taking a difference of this previous difference. Okay. So you'll be taking yt minus 4, then subtracting yt minus 4 minus yt minus 8. Okay. So if you're able to follow this, you'll be able to follow how we are getting these terms here. You're lagging by 4 periods every time since you're working with quarterly data. Now, if it was monthly data, you would have had yt minus 12 minus yt minus 12 minus yt minus 24. Okay? Here you'll be lagging by 12 periods every time. Okay? Since there are 12 seasons, or how many of those terms are coming in a particular year. So this will be a second seasonal difference. So generally, if you have data which is showing seasonal patterns, what you might want to do first is take a seasonal difference of your data, okay, which is find out what is yt minus 4. Okay, transform your series this way by taking a first seasonal difference and see if it is stationary. If it is still not stationary, what you might want to do is take a first difference of your data. Sometimes it becomes stationary when you take a first seasonal difference, so then you need not go in for the first difference of your data. But sometimes you might need to take a first seasonal difference. If you find your data is still not stationary, then you might need to take a first difference of your data. Okay? Then you might find that it is stationary. If it is still not stationary, you can go in for further differencing the data. Okay? But generally, it is recommended that you do not do more than 2 differences. Okay? So if you're doing a combination of a seasonal difference and a first difference, so you've already differenced twice, so it's recommended that you don't difference your series any further. Okay, and you should stop with the process of differentiation or differencing your data. Any doubts or any questions about this? I hope you'll have understood. Any doubts or questions? Okay, you all don't seem to have any doubts. So, yeah. Now, earlier we had discussed a case where these seasonal terms or components, they're entering the model additively, but they could also enter the model in a multiplicative fashion. So this is similar to what we discussed for the components of a time series also. So here, if you look at this model, which has been written here, here you have autoregressive terms and they are non-seasonal autoregressive terms. Okay? You can make that out from the lag that we have taken. Now, if you look at only this part, this is the non-seasonal moving average part. Okay, the first bracket and multiplied by ET. But you also have seasonal patterns in your data. So maybe your data is best modeled with seasonal moving average terms, because of which you also have a seasonal moving average component here. Okay, you can see that from the fact that you're going to lag your error term. Okay, you're going to take the fourth lag of your error term here. Okay, so if you expand this, here we are using the lag operator to simplify it. Now, if you expand this, okay, this is what you'll get. And finally, this will be the model that you will be estimating. Okay. So now if you look at the last equation, I'll give you a minute to work this out for yourself. Okay, so if you've understood this, can anyone tell me which are the non-seasonal terms and which are the seasonal terms which are coming in here in this equation? Assume that you're working with quarterly data.
I think anywhere the fourth lag is coming in are the seasonal terms.
Okay, yeah. Okay, so this is yt minus 1. This is the non-seasonal part. Okay, this is also the non-seasonal part. This part is the seasonal moving average component, okay, that you want to estimate. Now, again, this part, if you look at this ET minus 5, you might be wondering what this is. So if you look at the coefficients here, beta 1 and beta 4. So beta 1 is the coefficient of the moving average term at the first lag. And this beta 4 is the coefficient of the seasonal moving average term. Okay, so when we are writing this particular term, we are assuming, or we are saying that there is a possibility that our seasonal and non-seasonal components are going to interact with each other. Okay. So this term, okay, beta 1 into beta 4, we can just call it beta 5. Okay, that will capture the interaction between the seasonal and the non-seasonal components. Okay. So multiplicative models are generally considered to be a richer description of the data. Okay, it helps you to understand the data better or describe the data better, because it allows the interaction of the seasonal and non-seasonal components. Here you don't see these kind of interaction effects in the additive models. Okay, so in R also, I'm not very sure about this, but I think the seasonal pattern that we see, it is of the multiplicative type. Okay, so when you are estimating a Sarima model, I think the components will be entering in the multiplicative fashion. Okay. So I hope you all have understood this. So when we come to the ACF and the PACL, okay, let's just look at this. I'll mail this to you all a little later. Okay. I don't expect you to read everything here, okay, but this is similar to what we had discussed in the previous table, so I won't go through that. Just look at this part, identifying the seasonal part of the model. Okay. So this particular rule, it says if the series has a strong and consistent seasonal pattern, then you must use an order of seasonal differencing. Otherwise, the model assumes that the seasonal pattern will fade away over time. Okay. So this already, you can see that since there is a strong and consistent seasonal pattern in our data, you can expect that we'll be doing at least one seasonal difference. Okay. Then, however, never use more than one order of seasonal differencing or more than two orders of total differencing, seasonal plus non-seasonal. Okay, so this is what I was talking about earlier. So just keep in mind that we can only seasonally difference our data once. Okay, and we should not do more than two orders of seasonal, total differencing. If it's a combination of seasonal plus non-seasonal. Then if you look at rule number 13, okay? So if you look at the ACF, if you find that if the autocorrelation of the appropriately different series is positive at lag s, where s is the number of periods in a season, then consider adding an SAR term to the model. So if you find that there's a positive autocorrelation at lag s, which is significant. Okay, so since we have monthly data in our ACF, if we find that there are significant autocorrelations at lag 12, lag 24, lag 36, and so on, then we should consider adding at least one seasonal autoregressive term to the model. Now, if the autocorrelation of the different series is negative, okay, just a minute, I'm getting a phone call, I need to answer it. Just give me a minute. Yeah, sorry for the interruption. Yeah, so it's saying that if you find that there is one negative autocorrelation, okay, so at lag S again, so at lag 12, 24, 36, then we can consider adding a SMA term, okay, seasonal moving average term to the model. Now, the latter situation is likely to occur if a seasonal difference has been used, which should be done if the data has a stable and logical seasonal pattern. And the former is likely to occur if a seasonal difference has not been used, which should only be appropriate if the seasonal pattern is not stable over time. Now, since our seasonal pattern is stable, okay, what you will infer from this is that we need to do at least one order of seasonal differencing. You should try to avoid using more than one or two seasonal parameters in the same model, as this is likely to lead to overfitting of the data and or problems in estimation. So at the most, we should use one or two seasonal parameters. Okay. So just keep this in mind. I'll leave this open for you all. Just take a quick break and then we'll return to the practical part of it. Okay. Just take a quick break for 5 minutes. It's 3:33, so we'll meet at 3:38. Okay. Okay, I hope you all are back. It's 3:38. Okay, so can we resume the class? Yeah, I think we can continue. Okay, since it's 3:38, let's continue. So what we understood is that we will need to do at least one seasonal difference, okay, of our data. Now again, if you look at the ACF, okay, let's see the here we have a sharp positive spike at lag 1. Okay, so we might consider adding a moving average term. Generally, if you look at the ACF, okay, if this says autocorrelation of the difference series is negative at lag s, consider adding an SMA term to the model. Yeah, and if it's positive, then consider adding a SAR term. Okay, but since our data is not differenced, okay, we can try both. Since we will be using the method of trial and error, we can try both and then progress from there. Okay. So let's first seasonally difference our data and then continue from that point. Okay. So in order to do the seasonal difference, just create a new variable which will be the seasonal difference. Yeah. So I'm designating my variable this way. I don't want to, and I'll put the double D, seasonal difference of this DTLY1. Okay. Now, since we have monthly data, let's take it at lag 12. Okay, so what we are doing is YT minus 12. We are taking the first seasonal difference here. Okay. So now that we have taken the first seasonal difference, let's look at our data again. So you can use this command, which will give you a plot of the time series itself and also the ACF and the PACF. Okay. So now if you run this command, just look at your graph again. Okay. Now this data appears to be stationary once you've taken the seasonal difference. It already looked like it was stationary, but here you can see that the seasonal pattern is not so strong now. Okay. Now, in addition to that, if you look at this plot, okay, of the ACF and the PACF, here you can see a spike at lag 1. Okay. And you can see another spike in the PACF at lag 1 again. Okay. Now, what about spikes at the seasonal lags? Okay. So here at 12, you have a sharp spike still, and even here. Okay. Let's try and increase the lags. Okay. So here, if you look at it, at lag 12, there's a sharp spike in the ACF, but at lag 24, there's no spike at all. Okay, so the autocorrelation is basically 0 at lag 24. And here also at lag 24, it is not significant, the partial autocorrelation. Okay, so we can assume that the first order seasonal difference should be enough for us, and then we can go ahead and estimate our model. Okay, so based on the pattern in the ACF and PACF, could you all suggest what order of the model you'd like to try?
Maybe 12.
At lag 12, is it? So do you want to add a seasonal moving average term or seasonal autoregressive term? That's what I'm asking you.
Ma'am, I'm not sure. So you're asking what seasonal trend I should add, right?
Not seasonal trend, seasonal term. Like for example, if I'm adding, if you look at this, let's see. Okay, this doesn't have that. What I'm asking you is to determine this PDQ and PDQ. Okay, now we've already determined the D part. Okay, so in the non-seasonal part, our D, small d is equal to 0. In the seasonal part, our D is equal to 1. Okay, that's the first seasonal difference that we took. So now by looking at the ACF and PACF, I want you all to try and guess what could be the non-seasonal autoregressive order, non-seasonal moving average order, and the seasonal autoregressive order and seasonal moving average order. Okay? You can set this as 0 also, there's no problem, but I just want you to tell me possible values of the small p, small q, p and q. So you can use this table, okay, for identification. I've already mailed this to you all. Or you can use this also. Okay, look at the graph in your own R interface. Okay, and then try and determine what will be P and Q, small p and q, and what will be capital P and Q. Okay, so first the seasonal part seems somewhat easy, right? Okay, so let's, for the time being, we can start, since you have a negative spike here at lag 12, we can start with one seasonal moving average term. Okay, right?
Ma'am,
Yes,
we choose P and Q on the basis of graph, ACF and PCF, right, ma'am?
yes.
So, ma'am, basically, when the graph is moving downwards, so that is the point we have to take the lag.
Uh, Here, see, when you're saying moving downwards, you're saying once it decays, once it begins to decay, from that point you have to take the lag.
Okay, ma'am.
That's what you're saying, right?
Yes, ma'am. Yes.
Yeah, so generally the guidelines tell you that decay will begin, either geometric or oscillating will begin after lag Q in the ACF. That will help you identify the MA order, and lag P in the PACF. Okay? So that will help you to identify the AR order. So fine, if you want to start with the
Yes, ma'am.
non-seasonal part, okay, then let's just see this. Okay, so here, since decay is beginning after, let's say 1, 2, 3, okay, you might want to start with 3 here, okay, for the non-seasonal part, for the MA order.
Yes,
Okay, so
ma'am.
let's start with 3. And for the AR part, you have a sharp spike at lag, let's say 1, and this is probably 3, 4, 5, 6, yeah. So this is 3. At lag 3, you have a sharp spike and then it begins to die down. Okay? So what we can do is start with, I think, MA3 and AR3 and then keep narrowing it down. Okay, if that doesn't work, then we'll try and reduce by 1 and keep estimating. So it's a process of trial and error, and don't think that you're wasting time or you're just fooling around or you don't know what you do. This is how it is done in practice. Okay? Now for the
Okay, ma'am.
seasonal components or seasonal part, since you have a negative spike at lag 12, okay, let's assume that there's one seasonal moving average component, and yeah, here there's no positive spike in the PACF at lag 12 or lag 24. Okay, so we need not, for the time being, let's not add a seasonal autoregressive component. Okay, so let's
Yes, ma'am.
try with this. Let's start with this and keep estimating and see how our model is doing. Then we can reduce the number of autoregressive terms or moving average terms by 1 till we get the best fitting model. Okay, if this is not satisfactory. So I hope you understood how we are trying to determine the order of the model. It will be a process of trial and error and you will be guessing. Okay, there's nothing wrong with that. That is how it is done. So let's try and estimate this model now. Okay. So let's call it mod 1. Okay. And let's use this command arima. So the variable that we want to model is dtly. Okay. Just remember that. Don't take this one. Okay. Since you'll be specifying the order of differencing, you don't have to put this. Okay. SDDT. You don't have to put the seasonally differenced variable. Yes. So just put dtly1, that is the variable that you want to model. Then type order. Okay. So here you're specifying the non-seasonal order of your model. Okay. P, small p, d, and q. So remember that we said let's start with 3. Okay, for the AR component. We haven't differenced our time series. Okay. We took a seasonal difference, but not a simple first difference. Okay, and we wanted to start with MA3 also. So I've put in the order for the non-seasonal part accordingly. Then for the seasonal part, okay, just type in seasonal. Again, type in the order. Okay, so we said that we won't include an autoregressive term. Okay, so this is 0. We took one seasonal difference, so this is 1. Okay, and we decided, since there's a negative spike at lag 12, we decided to take one seasonal moving average term. Okay, so let's try and estimate this and see what are the results that we are getting. Okay, so just type in this command and hit enter. If you're not following at any point, you can stop and ask me.
Ma'am, should the seasonal be 1 or 12?
1. It automatically understands, since you're taking monthly data, it understands that the moving average term will be at lag 12. So it will be modeling ET minus 12 there. Okay, so it's the seasonal lag there. So it will be 1.
Ma'am, which library should I call for this ARIMA function? Because in my R it is showing couldn't find function ARIMA.
I think it is T series or stats. Okay, so just check if you've loaded. Stats is built in, it's already there in the library. I mean, it's already there in R. So just load it, and otherwise try T series.
I tried both with T series and stats. It's still not finding ARIMA function.
Ma'am,
It
it's in the
happens.
forecast library.
Okay, it's in the forecast library. Fine. Okay, try
Ma'am, can you
focus.
tell for GG as well?
Sorry.
For the GG or TS display and GGA
That is
AC.
ggplot2. ggplot2.
Okay, I tried with that, I guess. Okay, thank you.
Tell me if you're not able to estimate it, all right?
Ma'am, it was Arima is now working with forecast library. Thank you.
Okay. Thanks to the other student who mentioned it. Okay, one thing, there is also another package with a small a arima. Okay. So generally that does not allow you to include a constant unless you have small d equal to 0. Okay, so that's why we are not using it here. Okay, have you all typed this command? You all entered it?
Yes, ma'am.
Okay. So once you finish this, just type summary of mod 1. Okay, so this is the first model we are estimating. You can give it any name. Okay, so when you're doing your work, you can give it any name. I find it easy to name it this way. Okay, so once you type summary mod 1, okay, so here if you look right at the top, it's showing you that you have estimated an ARIMA model with 3 non-seasonal autoregressive terms, 3 non-seasonal moving average terms, okay, 1 seasonal order of differencing, 1 seasonal MA term, and that the periodicity or number of seasons, okay, that you're considering in a particular year is 12. So this is why we didn't put 12 over here. It already understands that you're working with monthly data, so you want to take lag 12. Okay. So this SMA here, it is ET minus 12. Okay. So now if you look at the coefficients, okay, you'll be able to determine if you divide the value of the coefficient by the standard error, you'll be able to determine which ones are significant, which ones are insignificant. Okay. So here you can see AR1 is insignificant, I think. No, wait, let's check. I think it's significant. Then this one is insignificant. This also is insignificant. Okay. This is probably significant. MA2 is insignificant, so we can drop it. Okay. MA3 is also likely to be insignificant, so again we can drop that. Okay. When we re-estimate our model. Now let's see. Look at the value of AIC. Okay, this was the model selection criteria, archaic information criterion. We want to minimize the value of AIC and BIC. Okay, for Bayesian information criterion. Okay, so can anyone tell me which coefficients are significant here? Divide the value of the coefficient by the standard error. Okay.
AR3.
AR3 is insignificant, right? I'm asking which ones are significant. Okay, because there are more insignificant coefficients. That's why I'm asking you which ones are significant. Anybody? See, if the t value, basically you're calculating the t value, okay, or t statistic. So you're assuming that the null hypothesis is that this AR1 coefficient has a value of 0. It's equal to 0. So when you divide, or when you're checking your hypothesis, you'll just be dividing the value of the coefficient, estimated coefficient, by the standard error. Okay. So if your t value is greater than 2, generally it's considered to be significant, your coefficient estimate. So which ones are significant now? Can anyone tell me?
AR1 is significant.
Yes. Then
I have to calculate the rest.
you don't really have to calculate. Some you will be able to understand visually looking at it. This is going to be insignificant, MA2. AR3 is going to be insignificant. AR2 is going to be insignificant.
Mostly with high standard errors would be insignificant.
Yeah. Okay. So here, so which ones are significant? AR1 is significant. Then MA1 is significant. And SMA1 is significant. Okay. Any others are significant? This AICC is AIC, the criterion, I think it's corrected for degrees of freedom. So either you can work with AIC or any of these, yes, but just note this down for your reference. Okay. For now, I'll just note down AICC 688.2. Okay. Is this all right? All of you understood how to determine which coefficients are significant?
Yes, ma'am.
Okay, so let's move on. Now let's re-estimate our model. Okay, but before we do that, let's do a quick diagnostic check of this model itself to see if this model is fine. Okay, so I've just written this so that I can remember that these coefficients are the ones which were significant, so I can use this information for my next model. Okay. Now just type this command. Okay. So here you can see that these are the roots. Okay, so characteristic roots of the unit circle. So if you remember our discussion when we were solving difference equations, we had discussed how if the autoregressive coefficients, if the sum of the autoregressive coefficients is less than 1, you can be sure that all the characteristic roots will be inside the unit circle. And a stationary series or time series is one which has all the characteristic roots within the unit circle. Okay. So now the way R defines characteristic roots, it uses the lag operator. Okay. And the roots that you get when you use the lag operator, okay, for example, if I have an AR1 model and I'm using the lag operator, then I'll have 1 minus A1L into YT. Okay, so that bracket part, 1 minus A1L into YT, if I take only the bracket and then solve or find what is the characteristic root, what will be the value of L there. Okay, set it equal to 0, that entire bracket, set it equal to 0, solve for L, then I'll be able to get the value of that particular characteristic root. Okay, so we had done this when I've shared the notes also with you all, but we didn't do it for the lag operator. Okay, we did it for the simple case of a difference equation which is written in the ordinary way. Okay, I'll just try and go back to the notes and show you all this. Yeah. Okay, so when you're finding the complementary function, right? Okay, so you use this method to solve the difference equation, and then you solve for b here. Okay? So b represents the characteristic roots. And in any equation, for example, in a first order difference equation, you'll have one characteristic root. In an nth order difference equation, you'll have n characteristic roots, okay, which are b1, b2, and so on. So now for an AR1 model, you'll have only one characteristic root, and that has to be lying within a unit circle. So if you remember, I had described a graph where you have imaginary numbers on the y-axis and real numbers on the x-axis. So if you look at this, it's doing the same thing. Okay? If you look at this autoplot mod 1, the graph which was produced, it is showing you a graph, and this is the unit circle which has a radius of 1. So all these characteristic roots have to lie within the unit circle. Okay? Now they are calling it inverse AR roots, but it is the same thing here. Okay? So this thing which I had shown you, I think in the previous class, let me see. Okay? These same roots, they are showing you that they lie within the unit circle. So for even the MA order, okay, if you look at the only the MA part of it, even those characteristic roots have to lie within the unit circle. Okay? Now the way R defines this, these are called characteristic roots, and if you take the lag operator and solve for L, okay, you can do it for an AR1 model, use any of the numericals that we solved. Okay, so if you take the value of B from that numerical and the value of L, where you've used the lag operator, you'll find that L is the inverse of B. Okay? So when you solve and find the characteristic roots using the lag operator, those are called inverse characteristic roots. Okay, but since R works with R works with lag operators itself when it's defining the model. So the characteristic roots using the lag operator itself are called the inverse characteristic roots. Okay, so that's why it's called inverse AR roots and inverse MA roots. If you're confused, just do what I said. Okay, just take a first order difference equation, solve for B, okay, where you have a number. For example, take yt is equal to 0.5 yt minus 1. Okay, and solve for B here, okay, using this method, and then use the lag operator and write the same equation, and then solve for L. You'll find that L is the inverse of B. Okay, so B is called the characteristic root, L is called the inverse characteristic root. Since there's only a first order difference equation, you have only one characteristic root, but R defines it in the other way. Okay, so it calls the roots from the lag operator, they call that the inverse characteristic root. So that's why these roots lie within the unit circle. Okay? And the actual characteristic roots will lie outside the unit circle. If you take this definition, this might seem a little confusing to you all, but if you don't understand it, then I'll write it down and show you all in the next class, okay, in tomorrow's class. Just give me a minute. So if you solve for these characteristic roots, they are supposed to lie within the unit circle. Okay? And if you solve for L, that's supposed to lie outside the unit circle. Okay? But because of the way R defines it, it will just be the opposite. The inverse roots will lie within the unit circle and the characteristic roots will lie outside the unit circle for R. Okay, so the main idea that you need to understand is that our model is showing that our data is stationary and that our model is fine, it is stable. Okay, although these are very close to the edge of the unit circle, but it's still not a problem. Did you all understand this, or did you all find it confusing? Okay, since nobody is saying you understood, I'm guessing that you found it confusing. I'll just write it down on a sheet of paper and then explain it to you all tomorrow. Okay? But this feature is interesting because it allows you to see this part about the characteristic roots lying within the unit circle. Okay? So you can conclude that our model is stationary, it is fine, it is stable. Okay? Our time series is stationary basically. Then after this, what you can do is check the residuals. Okay? So remember that for the Box-Jenkins method, we have done the first two steps in the three-stage process. So we did the identification part where you plotted the data, looked at the ACF and PACF. And then in the second stage, we estimated the model. Then in the third stage, you need to do the diagnostic checking. Okay, so here let's check the residuals from our model. So you can use this command to do that. Okay, check mod 1. Okay, check residuals from mod 1. So once you implement this command, once you run this command, you will get a plot of the residuals itself plotted against time. Then the ACF of the residuals and a histogram of the residuals. Okay, so the histogram is showing you that your residuals are more or less normally distributed. For the ACF, you can see it more closely. You can see that although there is a small spike here, okay, you can probably conclude that none of the autocorrelations of the residuals are at various lags are significant. Okay, so this is another criteria which has been met to indicate that the model is actually sound. Then a third criteria, if you run the Leung box test. So if you remember the null hypothesis of this test, okay, this portmanteau test, it basically has a null hypothesis that a group of autocorrelations, okay, if you test the null that these group of autocorrelations are statistically significantly equal to 0. Okay? The value of these autocorrelations together, they are equal to 0 statistically speaking. Okay? That is the null hypothesis of this test. So if you look at the p-value from our test, you find that you're not able to reject the null hypothesis. So the test is indicating that the residuals are not autocorrelated at various lags. Okay, so this is also indicating that our model is sound. So looking at only these diagnostics, you might be satisfied with our model. Since the residuals are model, it's indicating that our model is fine. But you might want to re-estimate your model and check whether you're able to get a model with a lower value of AIC and BIC. Okay? So let's look again at which coefficients we found to be significant and then try and make our model more parsimonious, okay, where we have fewer coefficients in our model. Let's see if we are able to improve the fit of our model. Okay? So let's try another model here, mod 2. Okay, again, use the ARIMA command itself. The time series that you want to model is this one. Then again, enter the order of the series. Okay? So this time we want one AR non-seasonal term to be there. The order of differencing is 0. Then one non-seasonal MA component to be there. Okay? Then for the seasonal order, we want only one seasonal moving average term, no seasonal AR term at all. So we'll set the seasonal AR term part to 0, seasonal order to 0. We have one seasonal difference, which we took already, and one seasonal moving average term. Okay, so now let's estimate this model. Okay, so once you run this command, then type summary mod 2. Okay, let's see if we're able to improve the fit of our model. Okay, so what you're finding here is, this time if you look at the value of the coefficients, your AR1 coefficient is going to be insignificant. Even your MA1 coefficient is going to be insignificant. Okay? And your SMA coefficient is this time significant again. Okay? If you look at the AIC itself, earlier you had got an AIC value of minus 688. Okay? Minus 688.2. So this model is not an improvement over that. Okay? Are you all able to get these results? Have you all got these results?
Yes, ma'am.
Okay, so maybe we should have included some other lags, or let's see, since only this coefficient is significant again, let's see what our diagnostic tests are telling us. Okay, again, do check residuals, and this time mod 2. Okay, so this is indicating that there's some problem with our model. Okay, the residual autocorrelations are significant here. If you look at the result from the Lume box test, you're able to see that you're not able to reject the, sorry, you're able to reject the null hypothesis that the residual autocorrelations are statistically equal to 0. Okay, so we are rejecting that null hypothesis. So at least one residual autocorrelation is significantly different from 0. ACF seems, again, you can see some spikes coming out here. So maybe this is not the best fitting model. The histogram of the residuals looks fine. Okay? So the indication is that this is not a good enough model. Now let's try and model with only the SMA term. Okay? Let's try and save these results. Okay, let's save this information that the SMA term is significant. Okay. Yeah, I've saved the AICC value here. So maybe instead of this model, let's try a slightly different one. Okay, so let's try two autoregressive terms and two moving average terms now. And the seasonal MA term, let's retain that. Okay, so I'm just entering that. Okay, now name it mod 3. Okay, run this command. Now let's see the summary of this model. Okay, what are the results that we're getting from mod 3? Okay, so here you can see that this AR1 coefficient is going to be significant. Okay, AR2 also is likely to be significant. MA1 is significant. MA2 is also significant. Okay, SMA1 is significant. Now, if you look at the AICC value, it has, you've been able to minimize it further. Okay, so for the first model, it was minus 688.2. Now it is minus 689.12. Okay, so we've got a better fitting model now. Just check the statistical significance of the coefficients. Okay, so what do you find are all significant statistically? You all have estimated the model. Are you all still estimating or can I continue?
Ma'am, we are estimating.
Okay. Just let me know once you finish. Okay, once you've estimated it, just check the residuals from your model again. Check residuals mod 3.
Yes, ma'am, done.
Okay. So what you can do is, if you check the residuals, if you have done the diagnostic checking, one thing you would have found from your estimation results is that all the coefficients are significant. Okay, right? Is that correct? What about MA2? Is it significant?
No, ma'am,
I didn't
MA2
check.
is not significant.
Okay, MA2 is not significant. So maybe there's scope for dropping that. Okay. So just remember that, but our model has got a better fit compared to the first model that we estimated. Okay. And if you look at the residuals, okay, diagnostic checking of the residuals, they appear to be normally distributed. There are no significant autocorrelations based on the ACF, although there's a slight spike here, okay, but it's not very significant even here. Okay, but you probably don't need to worry about it too much. And here you can see that the p value is quite high. Okay, so here we are not able to reject the null that the autocorrelations at various lags are statistically equal to 0. Okay? So they are not statistically significant. So we can be somewhat satisfied with this model, but we might want to drop the MA2 coefficient here, okay, since that is not statistically significant. Okay, so let's re-estimate again. This is how you'll be doing it. It's a process of trial and error. So you can keep doing it till you get the best fitting model. So let's just try one more, then we can stop with that. So this time again, wait, let me just, if you want to reduce your work, okay, what you can do is just hit the arrow key, the one which points upwards, the up arrow key. So it will keep showing you the commands that you typed earlier. Okay, so you can just modify those instead of typing the entire command out. Okay, so here we said that we might want to drop the MA2 term, right? The non-seasonal MA2 term. We'll retain the rest of it. Okay. So now estimate this model. We'll call it mod 4. Just do a summary of mod 4. Okay, here AR1 becomes insignificant. AR2 might also be insignificant. Okay, let's check. Yeah. Okay, so AR2 is also insignificant. What about MA1? Okay, so what we found is that this specification is not satisfactory because most of the coefficients are turning out to be insignificant. Only the SMA1 coefficient is significant. Yeah. So already we can we have some rough idea that our model is not very good. Okay? Again, if you look at the
Also,
AICC value,
AIC, yeah, AIC
yeah,
has also increased.
yeah. So that is another indication that this model is not the best fitting one. Again, you can check the residuals from your model. Okay, so you can see there is residual autocorrelation here. Okay, so our model is not satisfactory. So probably model 3 was the best fitting model. Okay, you can do some more permutations, combination of these and try to arrive at the best fitting model. Just let me know once you finish this and reach this point, check residuals model 4. Okay, once you have done this and you've gone through the results, just let me know.
Should I be getting the same values as you?
You're getting different values, is it?
Yes,
Ma'am,
ma'am.
I also got different values.
Like for p value, I'm getting 0.1103, and q star is 27.96.
Mm, what about the number of lags used? Total lags used is 24.
24. Yeah.
Okay. I don't know why that's happening.
Ma'am, for initial models also, I got different values.
Okay,
ma'am,
but
same.
the general conclusion is the same for you.
Yes, ma'am.
Which series are you modeling? Time series? DTLY1 only.
Yes, ma'am.
Yes, ma'am.
Can you quickly, one of you, can you share your screen? You'll decide amongst yourselves who wants to share
Muskan, you
it.
can do it.
Let me stop sharing mine. Yeah, one sec. Yeah, quickly share your screen.
Just a second. Yeah, ma'am, are you able to see?
Yes.
It's
Okay.
lit.
So the result you're getting is also different, right?
Yes, ma'am.
As in,
It's similar to my results.
okay. Just move up in your commands. What have you typed? Let me just see. Okay, the rest of you also check in case I missed something. Last time somebody else spotted what was wrong. Can you move up further?
Ma'am, it's a little bit different only. I can take a look at it. Like, it's not a major.
Can you go down? Just go down a little. Anyone spotted anything?
And I think the difference occurred when we dropped the variables, I guess. So it might be possible that we had more NA values than you, or I think. So if you can show the false true wala part, the number of variables we have.
That will be right in the beginning, but I doubt if it's that.
You can share your R file with us. We can compare it with ours. Can do that.
Okay, thank you.
Should I stop sharing?
Yeah, you
Ma'am,
can
for
stop
model
sharing.
4, even I am getting the same results as Muskan.
Acha. What about the rest of you? Are you getting the same results as me?
Yes, ma'am. I'm getting as well like you.
Okay. One thing you can do, I'll mail you the R code or R file, okay? But I don't know why that's happening. Let's see. Okay, we'll try and figure it out by the next session tomorrow. Okay, just one last part. For all of you who, since we've reached, I think it's almost 4:30, so we'll stop here for today. Go through this, see if there's anything that you did not understand, so we can discuss it tomorrow. Now, for all of you who were probably inwardly groaning and moaning that you have to keep estimating model after model and then seeing which one is giving you the best fit. Okay, it seems like a very long drawn, cumbersome process. So there is a shortcut which you can use, which we will discuss tomorrow. Okay? So we'll stop at this on this happy note today, and we'll continue tomorrow. Okay? So I'll see you tomorrow at 2:30. Right? Thank you for your time. We'll meet in tomorrow's class.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
You're welcome.